first of all, I'd like to thank the organizers for this opportunity to give a talk here. And I'm really delighted that I'm following Pedram's talk. It was an excellent talk with a fantastic introduction and, of course, final results. So the title of my talk is Critical Properties of the Prethermal Floquet Time Crystal. And this is work that has been done in collaboration with former NYU PhD student Matt Nutsche and Andrea Gambassi at CISA, and the results already appear in the following two publications. Okay, so as we heard in the previous talk, how do you define a Floquet time crystal? I apologize, I didn't realize that people at some point had decided to call it discrete time crystal, so I just always called it the Floquet time crystal. So the definition is that, let's say you have a Hamiltonian which has not continuous time translational symmetry, but discrete time translational symmetry. So it comes back to itself after some definite period, capital T. So we are talking about periodically driven systems or Floquet systems. Then the signature of a Floquet time crystal or discrete time crystal phase is that you have some order parameter, which I denote by O. The expectation value of that order parameter is periodic, but it doesn't share the same periodicity as the original Hamiltonian. It has a slightly longer period. So we were seeing in the previous example of period doubling, but there are other cases. You could have period tripling and so on and so forth. And that's not the only condition. You're really interested in a many-body system, not a zero-dimensional system. And so in a many-body system, you also want that if you look at, for example, unequal position, correlation, expectation values of this operator, then it shows long-range order. So expectation value of the operator O at some site I times the operator at some site J is non-zero as you make the distance between the two operators larger and larger. So you need both spatial structure as well as long-range order, and we have these three papers to guide us as far as this topic is concerned. So what I've always found very helpful is that there are many different kinds of Floquet time crystals. By now, there are numerous microscopic models, lots of theory papers, and if you open this review article, there is a table out here which guides you as to how to think about this particular phase. So what we heard about in the previous talk is the most stable Floquet time crystal. This is the one where which occurs in one dimension, and you have a disorder so that you have no heating due to many-body localization. But if you switch off disorder, there are examples of exactly the properties I talked about in the previous slide. But such a property will only be living for a finite amount of time, and the name given for it is prethermal discrete time crystal. And there's also these other kinds of time crystals which are known as mean field time crystals. Typically they arise when you take the n going to infinity limit of some model, and strictly speaking, in the n going to infinity limit, the system does show this kind of periodic behavior, but when you make n finite, then eventually heating sets in and the system does end up thermalizing. So you have all these different kinds of time crystals now. Not all equally stable, not all requiring the same amount of, some of them more sensitive to the initial state than others. So this is just like a nice table to guide you through in your journey through this topic. Anyway, so as we heard in the previous talk, perhaps the most stable discrete time crystal is the one that arises in one dimension. This is the Ising model with interactions. And to see this discrete time crystal phase, there are two very important ingredients. We heard about that. One of them is that you need disorder to prevent heating. And second, very important point is that there is an eigenspectrum phase in which every eigenstate of the Floquet unitary has a pair of the opposite parity, which is separated from it by a quasi-energy pi. And essentially, the two-point correlation function which detects this order is the one which makes the system toggle between the states with two opposite parities that are separated by this quasi-energy. You have a question?
One question about definition. When you talk about spatial order, and if you drive in Floquet time crystal everything with exactly same phase, so how you cannot have spatial order? Even if I have disconnected clocks, but I connect them to the same Boulder clock, it's my perfect Floquet. I will have perfect spatial order. I'm just trying to understand how you can destroy spatial order if you couple to the same cavity mode. You're just saying it's an extra ingredient, but to me, it's just almost guaranteed to be satisfied. Maybe I'm missing something.
Yeah, it's okay. I mean, look, I don't have a horse in this game, so I'm just telling you this is how people define it, and you can ask your question again. Yeah.
I mean, there's a paramagnet, there's two paramagnetic that they don't have. Same model, just different.
Yeah, I mean, I guess as far as the spatial order is concerned, it's the simplest example would be paramagnet versus ferromagnet. If you forget about the periodic drive, if you have a paramagnetic phase, unequal time will decay to zero, and unequal position will decay to zero, but in the ordered phase, it will be something non-zero. So what I'm trying to say is that this third line is the standard one for long-range order. But on top of that, you have this new ingredient, which is the middle line. That's all I'm saying, okay? Okay, so we saw this example many times, and I just, even though I don't plan to dwell on this much, I just want to say that it's always interesting. At least the way I got into this field is I never put in any disorder, and I was always looking at clean systems. And so you can ask what happens here. If I just make it clean, what would happen? So it turns out that even after the bulk order has gone away because of heating, so I'm talking about the interacting problem, which is Floquet driven, and as many of you know in the audience, you just have heating. So even after heating has set in and bulk order has kind of completely gone away, you still have interesting behavior at the boundaries of the system. So I would like to call that the prethermal boundary time crystal. And the way to see how that comes about is that think about just the simple Kitaev chain. So the non-interacting clean limit of this Ising model is just the Kitaev chain, and the so-called ordered phase is the one where you have Majorana modes at the two ends. And when you Floquet drive the system, then actually these Majorana modes can actually evolve into Majorana pi modes. And so if I just look at the quasi-energy spectrum of the clean Ising model with periodic driving, you have an enriched phase diagram where as you change the some amplitude to the drive, you can go from a phase where at the boundaries you have only one Majorana mode, and then you get topological phase transition to one where you have a pi mode, and then one where you have both zero and pi modes living together. And what's very interesting in these systems is that these pi modes or zero modes that you get at the ends of the Kitaev chain actually have a very unique property which don't arise in all topological phases of matter. They're known as strong modes. So they have if it's a zero mode, it has a property that it commutes with the Floquet unitary and it anti-commutes with the discrete symmetry of the problem. So if you have a zero mode, actually it implies an eigenspectrum phase. Every even parity state has its pair in an odd parity state at the same quasi-energy. And when you have a strong pi mode, then it is one which anti-commutes with the Floquet unitary, and it also anti-commutes with the discrete symmetry. So the existence of the pi mode immediately implies an eigenspectrum phase where every positive parity eigenstate has its negative parity eigenstate, but it's separated at quasi-energy pi. So even though superficially it looks like these edge modes must only survive in the ground state, it turns out actually they survive even at infinite temperature, at least as long as you're talking about the free limit. And what's really interesting is that once you put on interactions, they still survive for a very long time. So these are some plots showing you the autocorrelation function of the edge mode of the clean interacting Floquet system. Again, the bulk is at infinite temperature. There's no interesting long-range correlations in the bulk of the system. And yet, at the edge, you find that the edge autocorrelation function lives for a long time, it's like 10 to the 4 or 10 to the 5 drive cycles. And if you try to get a lifetime out of it, what you do find is that this lifetime is non-perturbatively long in the strength of the interactions. So this is just to tell you that you have all these situations where even when you switch off disorder, you can get certain autocorrelation functions to live for a very long time, even though some other autocorrelation functions may be decaying only within a few drive cycles. So now let me come to the main topic of my talk, which is, what about universality? I mean, so we by now, as theorists, we have seen many different models which show this kind of period double behavior. Yes, some are more stable than others. Yes, some are more sensitive to the how you prepare the initial state than others. But what about the transition from the trivial phase to the Floquet time crystal phase? Is there some universality associated with it? Can we get critical exponents and things like that? So this question has been addressed, again, mainly for 1D systems, because originally when people started talking about discrete time crystals, they were looking at 1D disordered Ising chain. And what they found was that there is some universality associated with the transition, and it's in the same universality class as the static disordered Ising model. So we decided to look at a model which is not in D equal to 1, but in D greater than 2. And so just to warn you, this is not a super stable time crystal, but on the other hand, it is a model which is very general, and it's you can use standard methods like large n and epsilon expansions and things like that to get at the critical exponents. So this was so our goal was to try and see if this model, what kind of exponents would you get out if you Floquet drive one of the most standard models for understanding the paramagnetic to ferromagnetic phase transition. So okay, so now I'm really coming to what the topic of the talk is. So what we looked at was the periodically driven ON model. So this is written for any arbitrary dimension D. So the parameters are, there is a scalar field phi, which has n components, and then there is a pi, which is the momentum, and V is the quartic interaction between the fields. And if I was not doing any driving, again, this is the textbook example for studying the paramagnetic to ferromagnetic phase transition. And so we are looking at the case where now you Floquet drive the system. So the particular thing we are Floquet driving is this detuning parameter R. We're Floquet driving it at some amplitude R1 and frequency omega. And I have to mention that this model was already studied by the following authors, where they did point out what the main phases were, but the universal properties were not discussed. So without interactions, there are two dimensionless energy scales that appear in the problem, dimensionless numbers that appear in the problem. One is the dimensionless amplitude of the drive. So remember, R1 is a drive amplitude and omega is a drive frequency. So twice R1 omega square is a dimensionless quantity, which tells you how strong the drive is. And there is another parameter here which tells you the strength of the detuning, again in dimensionless units. So if k is the wave vector of the modes. So let's say I take set k to 0, then there is a natural detuning parameter here, 4r over omega square. So what do we actually do in this problem? So first of all, it's best to just study it in the Gaussian limit. Yes, you have a question?
Yeah, I've got a couple of questions. The first is, I guess we're no longer in one dimension,
no.
Right? Because in one dimension, this thing wouldn't order.
Yeah, exactly.
Do you know if it's possible, has anyone talked about eigenstate order in, that breaks a continuous symmetry? Like, I've only seen eigenstate pairing of the type you need for time crystals in excited states for Ising or other discrete symmetries. So
no,
an instruction to.
No, I have not seen. I have not seen anything.
So it's a conjecture. This thing is relevant to.
No, this will give you discrete time crystals, except that you need fine tuning. Not every state.
Why is it discrete if it's got a continuous symmetry? Like
it is discrete because this is time. This is discrete in time, right? So the Hamiltonian.
It's discrete in time, but continuous in its internal symmetry.
Yeah, it's discrete in its internal symmetry. But usually, when people say discrete time crystal, they're talking about the breaking of the.
Yeah,
discrete.
Both things normally discrete.
Yeah. Okay. Yeah. So in this case, the spatial order is not discrete.
Okay. Thanks.
Yeah. But you can ask me the question again about eigenstate order. This one doesn't have the property of the 1D problem where every eigenspectrum has a pair which is separated from it by pi. There are only certain eigenstates which have that property. So you need to be, so it requires some fine tuning to be in the period double phase.
Okay, thank
Yeah.
you.
Okay. So, so now let's study this problem first with the interaction switched off, because we know from our intuition from undriven models, you can already get a lot of information about whether there's any emergent long-range order by studying the problem at the Gaussian limit. So we switched off interactions, and then you just have to solve this classical equation of motion. You need some initial conditions. So we took initial conditions where initially the system is in the ground state of the undriven model with very large detuning. So the initial state has very short range correlations. And then we time evolve it with respect to this periodically driven system. So due to Floquet theory, you can write this F as a part which is completely periodic in time and a quasi energy e to the I epsilon kt. And you have to solve, even for the Gaussian problem, this is a hairy problem to solve because you have to find the eigenfunctions and eigenvalues of this huge matrix in Floquet Samba space. So, but if you make approximations such as the drive amplitude is sufficiently small, you can truncate this huge matrix in Floquet Samba space. And what you will find is that depending upon the drive amplitude and the drive frequency and also the wave vector of the modes, there are some stable solutions and there are some unstable solutions. So this is the stability phase diagram. It is also a very well-known phase diagram known from the 1940s. It's known as the Mathieu equation phase diagram. This is because this is just nothing but the Mathieu equation. And what you find, so let me walk you through this stability phase diagram. So on the x-axis, you have strength of the drive, a dimensional strength of the drive. On the y-axis, you have the detuning parameter. So just look around this vertical axis where the drive amplitude is very, very weak. Then you have nothing but the undriven problem. And then you know exactly what's going on, right? Because when R, the detuning is negative, you just have modes that grow exponentially in time. And so it's completely unstable. Whereas when R is greater than 0, then you have a stable solution. So everything, all the blue is stable and the red is unstable. But now when you begin to Floquet drive the phase, then you begin to see a little bit more structure. Even in the stable phase, a part of the parameter regime which was stable in the absence of the drive begins to develop instabilities. And this is visible through the appearance of these red regions. And it's easy to figure out where these instabilities are showing up. These instabilities are showing up each time you satisfy the condition for parametric resonance. In other words, whenever an integer times the drive frequency is equal to the energy to create a pair of excitations, one at k and one at minus k, you'll begin to develop an instability. And so when you set k to 0, the lowest frequency at which this happens just corresponds to these points, 2, 4, and so on and so forth. When you make the drive amplitudes larger, then these these points of instability just grow larger and larger. Yes.
Why don't you have a two-particle continuum? Because you'd think that, you'd have an onset where, for instance, twice R, and then you'd have sort of be able to create pairs of excitations at k and minus k. Even
so that is why it's 2 times square root of R, because a single excitation is square root of R.
Yeah, exactly. But I'm just wondering why you don't create, if you can create pairs of excitations, why do you have to create them at k equals 0? You could always create them at k minus k, right? So
yeah, you can create it at any k. But the thing is, what's plotted here is this whole thing is just you can think of this whole thing as a parameter, R plus k square. So a y-axis is written. Yeah, exactly, okay. Yes. But physically, what matters to us is this lowest frequency at which the instability sets in. Yeah. Any other questions? Okay. So basically, what you find is that with drive, the stability phase diagram becomes extremely complicated. Without drive, remember, you just have one stable region for R greater than 0 and one unstable region for R less than 0. With drive, it just breaks up into these little bands. And what's also very interesting about this phase diagram is that if you look at the lowest quasi-energy, which is which corresponds to the boundary this blue edge separating the allowed stable region from the unstable region, you have two different categories of solutions. One category of solutions are those where the quasi-mode comes back to itself after a drive period, and there's another where the mode comes back to minus of itself after the drive period. And so it's the minus modes which morph into the Floquet time crystals, and it's the plus modes which morph into the regular ferromagnet. So in other words, just again borrowing from what you might remember from your statistical mechanics course, when you have no driving, remember you have one unstable region and one stable region, and it's the unstable region which becomes a ferromagnet when you switch on interactions, right? Now with periodic driving, what happens is that if this A region becomes a ferromagnet, but this B unstable region becomes a Floquet time crystal, then the C region becomes a ferromagnet, and the D region again becomes a Floquet time crystal. So it just the phase just alternates, and you can see that basically is the boundary of the B phase, which has the mode oscillating at omega over 2, and the boundary of the C phase, which is oscillating at omega, then the boundary of the D phase, which is oscillating at 3 omega over 2, which is the same as omega over 2. Okay. So you have, so what we are going to do here is just focus on this critical line. And it's a critical line because it is in the A and Q phase. And we are interested in a quench where the initial state is the ground state for some parameter out here, which means that there's no driving and you have a very large initial detuning. So the initial state has very short range correlations. And then you just follow its time evolution with respect to this Gaussian model with its parameters tuned to be right on the blue line. So first thing is that you can work out the dispersion, and the dispersion has a lot of structure in it. So this dispersion has these three crossover regimes. In the very long wavelength limit, the dispersion goes as omega over 2 plus k bar. So the omega over 2 is expected because you have Floquet, because you need Floquet time crystal here. And moreover, the leading behavior is not k, but k bar. Basically what happens is that the driving really slows down the velocity of the quasi-particles. So k bar is related to k by square root of q over 2, where q is my dimensionless drive amplitude, and I'm working in the limit where the drive is very, very weak. And then when you take the, when you go from very long wavelengths to wavelengths which are comparable to the frequency of the drive, then you have a crossover to something more conventional. Epsilon k just goes as k. So I'll just remind you about this because what I'm trying to say is that with Floquet driving, even with in the Gaussian limit, there is a lot of structure to the dispersion. And then when we start looking at light cone dynamics and all, the fact that the dispersion has all the structure will begin to show up in the light cone. So how do the correlation functions look? So we do this quench, and then what one finds is that the response function and the correlation function. So remember, these two in equilibrium related by the fluctuation dissipation theorem, but now we are not in thermal equilibrium. So they both show power law decays, and moreover, these power law decays are accompanied by the characteristic time dependence that you expect of the Floquet time crystal. It goes as cosine of omega t over 2, cosine of omega t, omega over 2 t prime. And the other information here is the square root of R naught factor. This is just the initial large mass before the quench actually took place. So already at the Gaussian limit level, you can see that there are all these power laws that are appearing in the 2-point functions. And it's kind of interesting to ask how do these 2-point functions relate to a similar quench you would have done in the undriven model. So this is something that has been studied a lot for the last 5 or 6 years. Suppose I just start with a system with very short range correlations, and I just do a quench near the usual static paramagnetic ferromagnetic critical point. How do the 2-point correlations evolve in time, etc.? And it turns out that the Floquet time crystal versions and the static versions are kind of very similar to each other. they more or less have the same form in momentum space as long as you rescale the momentum by this factor of square root of q over 2, and you multiply all the times by this periodic time dependence. Okay, and so now again, still continuing on the Gaussian part, let's look at the light cone dynamics. So this is just taking the Fourier transform of G and plotting it in x and t, and you can see that indeed, because of that complicated dispersion I was trying to describe to you, there is actually no single light cone, but there are actually two light cones. One is a smaller velocity, which has to do with this strong renormalization by the drive amplitude. And then there is a faster velocity, which had to do with the intrinsic quasi-particle velocity in the absence of the drive. So there's a little bit more structure. And moreover, in order to see the fact that the system is has period doubling, it is better to look at unequal time correlation functions. And so this is an example of an unequal time correlation function. You see both period doubling in time and this appearance of two different light cones. Okay. One last point I want to make about the Gaussian theory before I put on interactions is that in the Gaussian theory, you can also construct the Floquet unitary. And so this is the Floquet unitary between 2 times T1 and T2. And it's convenient to write it in this way. A middle part, which is completely time translation invariant, is the so-called Floquet Hamiltonian. But it's dressed on the left and right by these kick operators, also known as micromotion operators. So the Floquet part, which just mimics the quasi-energy spectrum, is kind of very standard. It looks like that of our ordinary harmonic oscillator with a dispersion which is just k bar plus omega over 2, where the omega over 2 is the period doubling part. But the kick operators actually have more interesting structure to it. The first thing you notice is that it's got these A dagger terms. I mean, this is expected. You're doing parametric pumping, so that's why they appear naturally there. And moreover, their effect is to do the following. So you are parametrically pumping the system. So if I look at phi square expectation value, that is becoming pretty large as compared to what its value is in the absence of the drive. So you might ask, okay, but what about the pi square, where pi is the momentum? Pi square expectation value, is that also very large? Because if both phi square expectation value and pi square expectation value is very large, it's like having a very high temperature state. But remarkably enough, that's not what happens here. It turns out that the phi square expectation value is very large, but the pi square expectation value is very small in such a way that the product of the two uncertainties is still the minimum uncertainty condition. So this is what is known as squeezing. And so that's what's shown here. You find that if I look at how the modes behave as a function of k at long wavelengths, because you're close to the condition for parametric pumping, you see the appearance of squeezing effects. But at larger k, this squeezing goes away, and the phi square and pi square quadrature is similar to that of the ground state of a harmonic oscillator. Okay, so now let's just look at the, yeah. Oh, yeah.
Squeezing. Am I correct that in the Gaussian limit, this squeezing would nominally continue forever? You kind of get a squeeze per Floquet cycle that kind of runs off forever?
No, this is stable here because this is, yeah, no, I mean, there's nothing that, there's no interaction here.
Right on the instability line.
But I'm slightly on the ordered side of the instability right now.
Okay, so it really does cut itself off even without.
Yeah. Yeah. I mean, that's the point of the Mathieu phase diagram, Mathieu equations phase diagram. There are stable regions and there are unstable regions in the Gaussian limit.
Right. I thought you were right on the cusp between them, so I thought you would have some sort of critical regions.
I'm on it, but slightly to the stable side. Okay. Yes. Okay, so now I'm running out of time, so let me just tell you the effect of interactions. So I will just tell you pretty much what the results are, since there isn't much time. So the reason why we can do this, the effect of interaction, is because we have this large n parameter. So basically, we just do self-consistent Hartree-Fock. And then among the results that we can get out is how the correlation length diverges as you approach the critical line. And we find that this exponent is given by that of the static Ising model, which is 1 over d minus 2, where d is the spatial dimension. You can also ask what happens if I apply a slight initial magnetization. What you find is that this initial magnetization oscillates with half the drive frequency, and it grows with an exponent beta, which is equal to half. You can also get out the fixed point value of the interactions in an epsilon expansion. This is the value you get. And so while these are more or less equilibrium static critical exponents, there is a purely out of equilibrium exponent known as the initial slip exponent. What it does is it asks the following question, that if I started from a strongly disordered phase and I quench to a critical point, then we know that at the critical point there is no energy scale in the problem. So everything should show scale invariance, should show power laws in times after the quench. And so what is the exponent which determines these power laws? And it turns out that this exponent theta can also be determined in this problem. It's equal to epsilon over 4. If you want to know what the functional form of this aging is for these two-point correlation function, this is how it looks like. This is the retarded Green's function at long wavelengths. So in the completely non-interacting theory, when one time is much greater than the other, this quantity at k equals 0 grows with t. But with interaction, this growth is actually slowed down by an amount which is equal to t prime over t to the theta. And so that's a standard example of aging. So you see similar physics here for quenches to the critical line. The last thing I want to say is that when I gave you results for what the exponents nu and beta are, the way we did it was the following, that you look at how the periodic drive, the interactions is renormalizing the parameters of the Hamiltonian, and then you just follow the effect of that renormalization on a Floquet eigenstate. So you're always assuming that you are initially in a Floquet eigenstate, and you are seeing how that Floquet eigenstate changes when you begin to put in the interaction. But in reality, of course, if you are in an initial state and you're driving it, then there is no guarantee that you stay in an eigenstate even in the presence of the drive. So the question is a lot more complicated than maybe the way I presented it. Here there are two questions. One is one of them is having to do with the kinetics of the phase transition, right? So you're starting with an initial state which is very short range, which has very short range correlations, and then you're asking, how does the system approach the Floquet time crystal critical line in the presence of interaction? So that is not very easy to answer, but what we do see is that if I don't assume that the state remains in a Floquet eigenstate, but I just look at the response of the initial state to a tiny perturbation which has this particular form, has the same periodicity as the drive, then the response to that perturbation ends up having some unusual properties. One of them is that it can resonantly create excitations at Kavli. And so when you look at the spatial two-point correlation function, it shows not only oscillations in time, but also spatial oscillations corresponding to these excitations that are being resonantly created by the drive. So these plots are just to show you that what we have actually not done is answer the question of, suppose I switch on interactions, how does the system end up going to the new critical point in the presence of these interactions? That is a much more complicated problem, and it seems that the way it would approach that new critical line is through the appearance of these kind of spatial structure, where not only things are oscillating in time, but also they're oscillating in space with a wave vector which is related to the drive frequency and the intrinsic quasi-particle velocity. So the last thing I want to say is that we spend a lot of time trying to do the problem numerically, and the problem with the numerics is that if the drive amplitude is too weak, for us to do analytics, the drive amplitude being weak was important, but in the numerics, if you make the drive amplitude too weak, then you won't be able to see the transition. If you make it too large, then all these higher Floquet harmonics begin to kick in, so that any universal transient behavior is only observable for a short period of time. So my student did manage to push the numerics quite a bit, and indeed there is a certain time window where one does recover the aging exponents that we got analytically, and indeed so you do find that this theta is the value that we got out. But we did not see this behavior over a long period of time. Moreover, we only see it for a handful of dimensions. So this numerical treatment of the problem is still an open question. So with this, I'll just present the conclusion. So what we did is we studied the so-called prethermal Floquet time crystal in the large N limit, and we showed analytically the appearance of some universal physics near the critical line. The exponents are found to be identical to the ones in the absence of the drive, except with the new blemishes that you have these, this period doubling prefactor. The numerics are not very easy to do, but there is some preliminary results which show that at least the aging exponent agrees with the analytic results. And the extensions, yeah, there are many of them. You could try to think about open systems and try to look for other universality classes besides Eisen. Okay.
Nice talk. Questions?
Can I ask a question? So in this interaction part, I just wonder, I assume there should be some version of like approximate Floquet Hamiltonian, which is static. I just wonder if you try to do like RG on that Hamiltonian, will you get similar results, or driving is really crucial, it changes all RG scheme completely?
Yeah, I don't know. We tried the RG, but we have to still think about the RG. What we found the easiest to do was just do the Hartree fork and going to infinity.
But say Hartree fork, did you try to do like an approximate, basically stroboscopic Hamiltonian, right? You introduce Floquet, you might say it's a Hamiltonian which describes every period, or maybe every second period, I don't know. And if you try to do Hartree fork on that Hamiltonian, is it similar or it's different? Because I see in your equations time always shows up, and if you do stroboscopic procedure, time should disappear.
Yeah.
And I'm just curious how different it is.
I think it is similar. I mean, here the only thing is that we've assumed that there are only two harmonics present in the time evolution, and well, okay. So I mean, I can tell you how we tried to do the interacting problem, right? So basically, you just solve this Hartree-Fock equation, which says that. Let's see, did I write it here? Where we just say that the prefactor of the mass term, gets self-consistently renormalized by this U phi square, and we try to solve that problem self-consistently. But I don't think that it should matter too much, I mean, if you're doing Hartree-Fock, it shouldn't matter how you're doing it. It's just the RG thing that we haven't got figured out.
Okay,
Yeah.
Thank you.
So I'm sorry, I did kind of lose a little bit right around the time you made you speed up.
Yes.
I don't understand what you mean by these critical exponents, because I guess statement number one, it's a prethermal time crystal. It's unstable. What is meant when you write nu? What is there a phase transition between, and how are you defining it for this kind of prethermal phase?
Yeah, so what this nu means is that you reach some kind of steady state in the problem. So let's say I'm looking at it stroboscopically. Then I expect the two-point correlation function to be e to the minus r over some length scale psi. And the new exponent is just saying how this length scale diverges as you approach this critical line. So that is the definition of the new exponent. But like I was warning you, what we have not done is studied the kinetics of the phase transition, which is a lot more complicated question, which is that you start from an initial state and you just follow how GK evolves in time, and then you see that it is approaching this kind of a functional form with psi taking this value. That is not something that we have studied.
I guess I don't understand what's prethermal about the time crystal and what are the phases.
The only thing prethermal about is that we are assuming that n is infinity.
Okay.
So basically,
for the mean field integrable n equals infinity model, this is
exactly. Yeah, exactly.
And this is within that.
Yeah, exactly. That's right.
Okay.
So that is the new exponent, and then you can put in a little magnetic field and ask how that grows as you approach this. This critical line, yes.
So actually I do have one question. So in this other work that you mentioned in quench dynamics, starting from this disordered state, you got this effective temperature somehow proportional to the initial gap in the system.
Yes.
So what is the effective, if you have a notion of effective temperature, what would be, is it like my intuition is right, that since the system is being driven, it becomes thermal, so effective temperature is proportional to the amplitude of the drive?
No, we found that there is not a good effective temperature description here. Because if you try to look at the response function and the correlation function, they don't end up being proportional to each other with some number out front. And the reason is that there are two different, energy scales in the problem, because you have, there's omega equal to 0 and then the omega epsilon minus omega over 2 type thing. And what I'm trying to say is that when you have many different quasi-particle excitations, it's not always true that you can define an effective temperature. Right?
Sure,
right.
But the universal behavior is thermal, so that should come from some sort of exponents.
Yeah, so all that I can say is that if you just look at the Keldysh-Green's function, it goes as 1 over k square. And so it is like the classical problem, so the upper critical dimension is 4, like the classical Ising model. But I cannot take these two things and force a effective temperature out of it, that's all.
Sure, that I understand. So actually, so R0, is that?
That's the initial mass.
And Q squared?
Oh, that's the drive amplitude.
Okay.
Yeah.
So
but what I'm trying to say here is that look at the way this time dependence appears. So if I Fourier transform it, there are things oscillating at k plus omega over 2 and k minus omega over 2, right? They're not just one scale, k. And so you cannot, you might get an effective temperature for one of the pairs of energies, but not for all of them.
If you go to the appropriate rotating frame, would it make sense to define that?
We didn't try too hard because I'm not very wedded to the idea of an effective temperature. So I don't know what it buys you, but I feel like there's more information just when you have the 2-point function. And the fact that this goes as k squares, it tells me enough that, yes, this is, the upper critical dimension is 4 and not 3, for example. Yeah. Thank you.
More questions? If not, let's thank Aditi again.
Yeah.
We'll come back in half an hour.